How are you?
Good, thank you. Did you get my email?
Yeah, that you need to leave. Oh, that's okay. Completely understand. We're recording. It's going to be a little tricky to get through mathematical examples on the recording, but I think that I have it covered. So cross your fingers. We should be okay.
Okay, thank you.
Well, you need to find like, you need to find something that describes people literally coming there.
Okay, guys. Folks online, can you hear me okay?
I can't. I'm trying to think of how we can go about it. You wanted to.
Okay, awesome. Thanks guys very much. And I'm assuming you can see the screen okay when I put the slides up. Let me do that right now. Okay, good. Let me know if anything changes. Oh wait, I don't think I have the sound up on this machine. Hang on. Not very high. Okay. All right, there we go. That should be all right. Okay, guys. So I put some handouts. I usually don't like to pass out a lot of paper, but for what we're going to do today, it might just be easier with the handouts. So I apologize if anyone is offended because of the paper use. So what I have passed out is a reference sheet with some formulas on it, and a tutorial that is also posted out in Blackboard specifically for Bayes' theorem and working Bayes' theorem problems. So we're going to sort of pick up where we left off and on the lecture about clinical data that included test characteristics, and take that a little further and use that information in calculating conditional probabilities with Bayes' theorem today. So anything before we get started, guys?
Our posters.
Yeah.
Sorry, it's been a very busy day with lots of things going on. I've been running since like 4 or 5 in the morning. When are they doing that?
So the actual poster session is December 8th. It's a Friday, I think, and it's like from noon to 2 or something like that on the syllabus. And so you don't have to turn anything in, just show up with your poster. And I do want to reiterate, it does not have to be fancy or expensive, all printed on one big glossy sheet of paper.
Now, is that for just this class, or is that part of like the research day thing?
So no, BMI Day is separate. That's on November 4th. So BMI Day is a recruiting event that we are doing for high school and college folks who might be interested in careers in biomedical informatics to build career awareness throughout the state. And so we've got about 120 people registered right now that are all going to descend on UAMS Saturday, November 4th. So for anybody that would like to come and help direct traffic and get people to rooms, that'll be a fun day with folks. Free lunch, obviously, but that's separate from the poster session.
So is the poster session just like an in-class?
Yeah, so I don't know exactly where we're going to hold it. Candidates would be the 10th floor rotunda of the Cancer Center, the open area, or out here in the hall, or the 12th floor of the spine building. Those are sort of our usual candidates for stuff like that. The institution provides cork boards to put posters on. And so bring your poster however you do it. If it's 8.5 by 11, a bunch of sheets to tack up, that is completely fine. However you guys want to do that. If you want to bring a projector and project it on the wall, that's fine. I completely don't care. And I don't want folks to have to spend a lot of money on making posters and stuff.
Okay.
So the prettiness of it, aside from, your artful use of visual display and graphics within whatever format you presented. The format does not matter.
And then the final exam, that's going to be like what, December 14th?
Yeah, is that what it says in the syllabus? Okay. Yeah, and that will be on Blackboard.
So it'll be a Blackboard-based test.
Yep.
Because me and Amy here have just been talking, we're waiting for the public health stuff where we're going to be like killer, and probably with this probabilistic, but we're concerned about, the earlier stuff.
Type A
And we're-
is concerned about getting prepared for the final
We're both
exam.
type A.
Okay, so I'll tell you what I will do. I took Tremaine's advice. Thank goodness y'all don't realize how much Tremaine has been at fault for the things that have gone well this semester. Tremaine recommended that we put all of the questions for the little quizzes and stuff in a pool. So I can go into Blackboard and make all of the questions from all of the quizzes available for study in one non-graded thing that you guys can take as often as you like.
Okay.
I had actually thought about doing that because I'm a little worried with the way that we're giving folks 3 attempts and the point earn back and stuff. I'm worried that folks are going to sort of cognitively kind of rely on that, and that having to take an exam where you don't get those extra chances on the final would be difficult. So I will put all of the questions in there, and so that you can take it and sort of self-assessment gauge your knowledge. The questions on the exam will be the same cognitive level as the ones that are on the quizzes. Like if something's at a worker problem in here and on the quiz, it'll be the same kind of difficulty worker problem on the exam. So the questions will all be the same format as you've had on the quizzes and similar cognitive level.
And then I had one more question. I'm sorry.
No, that's okay.
There was on the relational database quiz. There was one question that I could not for the life of me figure out because I don't know why I was struggling with it. It was the one that had like a statement, and it said, what is this? Is this a
Instance or universal.
no, I think it's universal. It was. Let me pull up right here. Look at it. At least I think I can look at it. It was, but it was asking for not ratio. It was the command itself. It was a prop or a provision or restriction.
Okay. A projection versus a restriction.
Can you look at that? Because I feel like when I looked up, like I said, my brain's fried right now. But I felt like when I was looking through and having played with SQL a little bit before, maybe I just wasn't reading it right because I didn't see any of them. I chose that none was an option, and that was incorrect.
Okay. I'll go back and check.
Yeah.
Okay, 2 of you had questions.
I
Okay.
through in a second attempt. I was like, well, maybe it's this other one, but really, because it was a statement that was calling all of the results, and then it was a restriction. So it was a selection and a restriction, but there was no selection restriction option.
Okay, let me go back and look at it, and I'll get an email out to folks.
I think in the slides, selection is restriction.
That will be true. that really is true.
All right.
You good? Okay.
I like my state of mind.
Okay, so at this point, I think that I am caught up on grading labs, so everybody should have gotten lab grades. I have not yet graded the discussion forum, but if you're participating and contributing, you can count on your 1 point. I will start getting caught up on those. I wanted to get the labs first so that folks could get feedback on that. I owe you guys a quiz for last week's content. I have it roughed out, but I don't have it entered in Blackboard yet. So I'll put the quiz in at some point this week, but needed to get through this stuff first. Yes, Miriam.
I don't know if I missed this. For the ontology lecture, was there a place for our lab to post it?
Oh, geez, somebody asked me to do that and I forgot. Yep, thank you. Let me write it down before I move on so I don't forget. And that was week 8. Thanks, Miriam. Okay, anything else before we get started? Okay, so at the start of the Bayes lecture, I think the main problem that the book sort of wants to get across is that reasoning by intuition in clinical practice can be misleading and wrong. And with that, I heard a ding. Okay, yeah, Mitra, Miriam just asked about it in the class. I need to get that posted. I guess you were the person that asked and I didn't get it posted, so I will, I'll post that. I wrote it on my hand. You're welcome. Sorry that I overlooked it. Okay, so this lecture, for those of you who like written sources, this lecture has those. For once, and it follows pretty closely the first half of the chapter in the book about Bayes' theorem. I don't think that we're going to get to the content in the back of the chapter within one lecture because I wanted to take some time and work some examples with problems. So just to start us off, this is the example given in the book. Basically was it in the early days of AIDS. If we had a test that was positive 98% of the time when the antibody was present, and the same test was negative 99% of the time when the antibody was absent, one might think casually that it's a pretty accurate test. Therefore, if a person tests positive, they're likely to have the disease. Pretty intuitive. It kind of makes sense. So what the problem is talking about is the first, of course, is sensitivity or true positive rate. And we're going to spend a little bit of time on this because in the last, when we went over test characteristics, I was using that term more casually than I should have, and Sally sent me an email. So I want to go through that with folks and make sure that we're clear on it and have included the way that folks use it in epidemiology. For the negative test, we're considering specificity or true negative rate. And so when you work that problem out, which we'll do in a few minutes, you realize that basically fewer than 10 out of every 100 people that test positive actually have the disease, which is sort of the importance of using objective evidence and actually calculating out this information rather than doing intuitive reasoning. So just to review a little bit, if we consider tests as a binary classifier, meaning that a test is being called upon to say whether somebody actually has the disease or not. So I call it the haves and the have-nots with respect to whether they have the disease. So up top is in a 2x2 table. So the top, they either have the disease or they don't. And then on the left-hand side is the test result. And so that naturally breaks things out into 4 categories: true positive, false positive, true negative, and false negative, where obviously the red ones, the false ones, are the bad ones. Everybody good? And I've left this on the little reference sheet as we go through the problems today. So to calculate it out, if it's the way that I calculate these out, and that we will do one example, I think, with the actual Bayes formula in here. I always use the trees and the tables when I calculate these out because it prevents me from making a mistake or a slip. And so I think about these in that way. So if we consider 1,000 people given the sensitivity and the specificity and the prevalence of the disease. So first off, out of 1,000 people with the prevalence of 1 in 1,000, so the disease arm is 1 and the not disease arm is 999. Everybody good there from the problem statement? Okay. So then if they have the disease, then we're looking at sensitivity. And so we want to take that 1 and we want the number of people, not whole people actually at this point, but the number of people that would test positive if they had the disease. So we multiply by the sensitivity, which gives us the 0.98. And then because with a binary classifier, they either have the disease or they don't. That's it. There is no in-between range. So 1 minus the 0.98 is the 0.02 on the negative arm on the top. Everybody good there? Okay. So then for the not having the disease, it's a similar thing. We multiply by the specificity and get the numbers of the people that would test positive versus negative who don't have the disease. So that's, have you guys worked tree stuff before?
I took the pharmaconomics and Dr. Martin. We did
Oh, good.
triation.
So you good.
It's a CEA analysis, basically. It's
Yeah.
just done with outcomes for a test.
Yeah. Okay, so some people, but not everybody. So then when we do the tree, basically what the problem is asking us is to calculate the positive predictive value, the percent of people who test positive who actually have HIV. And so in doing that, we can use the numbers that we get out of the tree to calculate the positive and the negative predictive value for those. So the formulas are on your reference sheet. And so remember what we said when we were going through the slides about the test characteristics, where it's really important to keep straight the denominators, which is the heart of my loose language. So on the top, you have the denominator for the positive and the negative predictive value are the number who test positive or negative. So the positive predictive value is the true positives with respect to the population of all positive. And so it's similar for the negative predictive value, the true negatives over the whole group that tests negative. So for the denominator of the positive and negative predictive value, it's all positive or negative respectively for those. And then on the other dimension, the sensitivity and specificity, the denominator is different. So I call the denominators the haves and the have-nots because the sensitivity is the true positive over the haves, which in the literature is what people call the true positive rate. I call anything a rate that's a numerator over denominator, which got me in big trouble. So don't do what I do. And so for the sensitivity and the specificity are referred to as true positive rate or true negative rate with respect to the haves and the have-nots, respectively. So it's not true positive over all positive, which would be the positive predictive value. So I think I've always wondered why they used different words to describe these. After having made that mistake continuously, I get it now. So even though it's a higher cognitive load to have to remember the different labels for the test, it's different because the denominator for those tests is different for those calculations. Of interest in biomedical informatics, the precision and recall are also aligned with sensitivity and positive predictive value. So I put those there too, because when you're talking about information retrieval from a database, like if you're doing retrieval on Google results or something, they don't call it sensitivity and positive predictive value, they call it precision and recall. So the words are different, the formula and the concepts are the same, so I stuck those up there for you as well. So this is your little cheat sheet. When you draw the table, if you ever have occasion to draw the table, like for those of you that might sit for the medical boards later, don't forget to always put the true condition at the top of the table. If you mix up the sides, you will get really confused if you try to use what you've drawn. Okay, so everybody has a copy. Does anybody else need a copy of that sheet? Okay. Okay, so why do people get the prior problem wrong? The reason why people get it wrong is something called base rate neglect, or it goes by these other names as well. But basically, the mind tends to ignore the former information and focus on what's more recent in the mind. And back in the old days at Duke, when Eugene Stead started the Duke Cardiovascular Data Bank, that is the reason why he started it, was because when clinicians are treating people, if they might have treated, 100 people with acute coronary syndromes over the past year, but the last one that came out of the cath lab that the physician treated is going to be the most memorable because of the recency effect. And so base rate neglect is sort of similar to that. It's the mind ignoring that previous rate. And so when considering the positive predictive value in that problem, the positive predictive value, it depends on that initial probability, because it's in the denominator of that equation. And so it takes into account what physicians and humans in general would normally miss due to base rate neglect. Is everybody good on that? Okay. So important, the base rate is the prevalence. For those of you who don't do a lot of clinical stuff or haven't yet, that would be a different concept than incidence. Incidence is new cases. Prevalence is all the people with disease, not just the new ones. So I coded prevalence purple for P, so I didn't forget it. So when we talk about a test and we're using a test as a binary classifier, a test is really not a binary classifier. The reality that we're representing as a binary classifier is up here on the slide, where there's some distribution of the healthy population and some distribution of the diseased population. And wherever you draw the cutoff value, because those two populations usually always overlap in some way, hopefully it's a kind of fortunate overlap like this here. When you draw that cutoff, you end up with some error, and that's the false positives and false negatives that you get in the test results. So when we draw that 2x2 table and we calculate those out, these numbers here under the overlap in the tails on either side of the cutoff are the numbers that we are calculating and concerned with when we talk about the accuracy of a test. And so aside from test accuracy, there's other cognitive biases that I wanted to mention that are also described in the chapter. The first is the representativeness heuristic. Is everybody familiar with the term heuristic? Basically, rules of thumb, sort of, that people use. So the representativeness heuristic basically says it looks at the probability that a patient belongs to some group. And so you have trouble when you make those decisions. So for example, if I know that that 50-year-old men who test positive for PSA, when they have a high PSA, that there's a certain percentage that they will have cancer. And so if I have that population and I know that percentage for that population, but I have another guy and I don't know how old he is, but I'm saying, 50, but maybe he's 30 and he just looks older. So there would be a representativeness problem with me saying, I'm the 30-year-old and the rate for the 50-year-old's close enough, because the rate that I would be using wouldn't be representative of my patient, because my patient is not representative of the group over which that was calculated. We're good? Okay, so there are problems when using that heuristic when, for example, when the condition's rare. Clinicians don't encounter it as much, and so it's harder for them to say whether or not this patient belongs to this class. You know, how typical is the presentation and whatever, if they're not seeing it very often. If their previous experience is atypical, so if you've got a clinician who's in the ED and for whatever reason they've only treated little old ladies that present with an infarct, maybe. Little old ladies tend to present differently with infarcts. If they're thinking about symptoms or a patient population for how men present, they may miss more, have representativeness bias, because the little old ladies that come in who present, their presentation is going to be atypical in a lot of cases, in a much higher proportion of cases than would men. So those are sort of the problems with the heuristic, and these are cognitive problems. There's a good article out there that goes into a much longer list of biases in human decision making that in the human-computer interaction course we'll go over.
Just a little classification bias.
Yeah. Yeah, exactly. So Sally says that this leads to misclassification bias in research, which is another bias on the long list of potential. Yeah. And so there are two other ones that I wanted to mention. The availability heuristic. Basically, it says that events that are more easily remembered are judged to be more probable. There are problems sort of similar to the last one with people using the heuristic when last experience was sort of atypical with patients or condition. When the last exposure was dramatic, it will be more memorable. Riding on an ambulance, I had a few cases that I will absolutely never forget. they might or might not have been typical, but to the extent they were atypical, I will have availability heuristic because I will forever remember those cases. If a physician's last exposure was very emotion laden, that's another sort of contributor to an availability heuristic, making those memories of those cases that were more prominent kind of burned in memory. And then the other one is anchoring and adjustment. So even if you use objective evidence and calculate out, like we did for the HIV problem, to try to counter against base rate neglect, unless you actually go forward and calculate out the number with the equation, it's very easy to not adjust your new probability in a corresponding way for the evidence. So if you get new evidence that should adjust your probability a big amount, but you only adjusted a little amount, that would be a problem with anchoring and adjustment. And it's usually in the case of people sort of stick to their initial assessment and that initial probability and tend to adjust less than they should when new information becomes available. And then the last is referral bias, which is similar to the first one, the representativeness. Basically, when a prevalence is used for a wrong population, like the example with the prostate cancer or the high PSA. And so the text gives several ways to avoid the biases. The main way is to use literature-based estimates for prevalence for your initial assessment. The second, they give an example of clinical prediction rules. For example, when you go through and based on how the patient presents, you have a little tool that you score it out, and then it says if they get a score between this range, they have this probability of having a condition. If it's between this range, they have this other probability, and maybe in this third range, they have a higher probability. So scoring rules can be used to make it more objective. And then the estimate, of course, may still be wrong because of representativeness bias or referral bias or something like that. But they're ways of trying to objectify the clinical decision-making process, which is pretty hard to do because, let's see, how many? Got one of our physicians in here. Like, Sally, how often have you ever calculated one of these out at the bedside? 0, goose egg. Right, so it's, even though the book does not come out and say that, I sort of felt it important to say, like, I've never seen a clinician at the bedside calculate this stuff out. Maybe in some extreme case somebody might, but there is a lot of subjective intuition that goes on with assessing probabilities and the likelihood of disease. And so when we factor that all into the process, the hypothetico-deductive approach that we talked about earlier, really what we're talking about is the top left, when the patient presents, after some initial impression, the physician starts coming up with a working diagnosis and kind of a mental gut feeling for what the probability is that the patient might have that diagnosis. And so that would be the initial probability. And then after using that and then that working diagnosis to figure out what tests to order, what additional assessments to make, then they're going to refine that probability. So this is between these two is where the anchoring and adjustment bias happens. When they get new information, there's not as much adjustment. But where this is going is that there is a way to formally calculate this, and that's what the Bayes theorem and problems that we're going to talk about today is a formal way of calculating conditional probabilities and of updating the probability based on new information that comes to light in assessing a patient. And so how that looks schematically, this diagram is also in your book, but I wanted to have it here so that we could talk about it. When a patient comes in, you get this initial probability. So the initial probability might be 50%, as in A, the top part of the figure. And then some test is performed. And after that test, you get new information that moves that post-test probability. I think one of the examples in the book are a patient that walks in that's having some ischemic problems, chest pain on exertion. And the doc says, well, let's do a stress test. So they do a stress test, and there's a positive result on the stress test, which increases the probability that the patient actually has a coronary artery disease and ischemic problems from that. And so the use of that test then enables a clinician to recalculate, rethink, add new additional information into that probability, that initial probability, which moves it to the right from 50% to further up closer to 1 based on the positive stress test in the example in the book. And so often there's not just one test, there's multiple tests that are done. And so when tests are chosen, tests are really chosen or should be chosen based on their ability to reduce uncertainty and weighing that against the cost and the risk of doing the test for the patient. So it's not like it's sort of a cookbook thing, but there's decision making about the likelihood of the test to be able to give a definitive diagnosis should one be needed. Does that make sense? You guys good? Okay, so back to talking about the test. So we've talked about cognitive biases that decision makers make. And if anybody is really interested in cognitive biases, the article by Crosscarry, there's I think an initial article and then one later in time that was published, really has become the definitive list of biases in clinical decision making that people use. If you're interested, I can send it, or you can probably just find it really quick. It's pretty well known as the Crosscarry article. So tests also have biases in addition to people. And so, but some of the same things are at play in the test bias. So the spectrum bias is similar to the referral bias that we talked about earlier in the representativeness bias, where a study population on which the test is based, because when you get a new test on the market, you do the studies that create the ROC curve for the test, and that let people know what the sensitivity and specificity are for the test at the cutoff value that's chosen. And so if the study population on which the test is based is different from the clinically relevant population, then there's a consideration. And this is key in the FDA's decision making when they're looking at applications that come through. I've had the privilege of working with a protocol team that's actually trying to get a test through the FDA, and their primary concerns were exactly describing the population on which the test was going to be tested and characterized, so that could be described very extremely explicitly in the label for the test. And the reason why they're so concerned at doing that is to prevent spectrum bias on the test, so that users of the test have it clearly stated in the labeling what the population is. The next test bias is test referral bias, and that's basically when there's a positive index test is used as a criteria for ordering a gold standard test. And so what all that means is that when an index test would be sort of the first test that might be performed, back in the bottom one here. So the index test would be perform test 1. And then there might be some gold standard test with better test characteristics. If it's the gold standard, it would have to have better test characteristics. And if you're if people only can take the second test after they have tested positive on the first test, then that's what they mean by the test referral bias. Then, because what that means is that the study population has a higher likelihood of disease. So, for example, in a drug trial, kind of different from test, but the same idea. If you're only testing a population that's failed on certain therapies, like in mental health for the antipsychotics, often they would only start them on an atypical antipsychotic if they had failed 2 well-controlled trials on one of the first-line meds. And so you see that sort of staged testing a lot in development, which is where the referral bias comes from. And the last one is the test interpretation bias. And that's basically when the interpretation of the test is colored by what the index interpretation was, or vice versa. It can happen both ways, which is why when you're doing a study to characterize a test, the gold standard evaluators are completely blinded from the other. So there's complete separation to eliminate test interpretation bias from the studies that are used in the test development. Make sense? I see a question. Okay. I'll be quiet while you process.
We're good.
So, a test referral bias, having like your rapid strep test and it comes back positive, that they send your
Yes,
testing on.
exactly.
But what's the test interpretation?
So that would be, so say a lady has a mammogram and they detect something that looks suspicious. And when the person interprets the second test that's done, then that person knows the patient's there because they tested positive on their first test. So that would be that the presence of a positive result on the first test impacting the clinician's interpretation of the second.
Because they know they got recommended, they're going to be extra.
Yep, exactly. So like if I walk into the doctor's office and say, yeah, I did this home pregnancy test, woohoo, the doctor's going to be extra careful because they're going to be biased. They're going to think that I probably really could be pregnant when they send the HCG off for testing. We good on the biases? Okay. So Bayes' theorem is an attempt to get rid of some of those biases. And first, we're going to talk a little bit about probability, and then we're going to spend the rest of the afternoon working Bayes' theorem problems. Yeah, it'll be fun. And hopefully, you guys online, I think I've got you covered. I hopefully have everything in the slides. So we're going to see how this works. It's kind of hard to work problems in slides. But we'll try. So just some housekeeping with respect to probability theory in case you haven't used it in a while. So probabilities of exhaustive and mutually exclusive outcomes, for example, tossing a coin, have to sum to 1. So there's one event and there's multiple outcomes. If it's a coin toss and there's 2 outcomes, they have to sum to 1. If it's some other thing and there are 3 outcomes, like the clinician's judgment of whether an adverse event was not related, possibly related, or definitely related to the drug, the probabilities have to sum to 1 because those are exhaustive and mutually exclusive. By mutually exclusive, you might have heard the word disjoint. It just means that they are non-overlapping in any way. Like if a coin is heads, it can't be tails. If it's tails, it can't be heads. There's 2 outcomes, that's it. And if you define those 3 outcomes for some other event, the idea is that you define them such that they're exhaustive and mutually exclusive. So that is what has to sum to 1. And we're going to use that in drawing the trees. Because as we go through and we have the information for one arm, and it's a binary outcome, guess what? 1 minus gives us the second arm, and it's a beautiful world. So the next thing I want to talk about is that if there are 2 independent events both occurring, for example, 2 coin tosses, So the second one is fundamentally different than the first one. And when people have problems with probability theory and statistics in intro statistics class, this is why, because they mess up these two in answering the problems. So for probabilities where there are two separate events, then you multiply the probabilities. If you want the events of, say, heads on the first and tails on the second coin toss, then you multiply, if it's a fair coin, 0.5 and 0.5, and you get 0.25. Everybody good on that one? Okay. And then the next one is conditional probabilities. So for the example here, the probability of Lyme disease given a target sign rash on the skin. And so basically, we want to know the probability of the disease given that this other event is present. What'd you say, Robert?
That this other event has occurred.
Yes, exactly. And so Bayes' theorem is the tool that we use when we calculate conditional probabilities. So a quick example, and the document that I handed out, hard copy in class, for those of you guys online, it's posted in the readings for the week. It's the Bayes' theorem tutorial by Mario Triola. I'm hopefully saying the person's name right. Literally, out of all the statistics books I've ever looked at, this is the best thing I have seen written on this. And I will forever use this because it made it easy for me. I hope it's the same for you guys. So if a Gallup organization randomly selects an adult American for a survey about credit card usage, if we just use subjective probabilities to estimate these, let's talk through them. So the first is the probability that the subject is male. So if we just give us our gut feeling, what do we think that might be?
Well, male-female population.
Yeah, given that we know we have distributions and we know we have stuff under the tails. So
50-50.
exactly, 50-50. Okay, good guess. So then after selecting a subject, it is, so there's our 50-50. So after we select a subject, we later learn that the person was smoking a cigar when they selected them. So how would that change our assessment? We know that more men than women smoke cigars, so that's going to enable us to subjectively kind of adjust our probability a little higher. So 85 is the guess that they make in the tutorial. If you'd have guessed 90 or 70, it would not have been wrong. It said subjective. So we can guess. So what we're guessing is the probability that the person chosen at random is male, given that we've also learned that they're smoking a cigar. You guys good? Okay. And so the last part of the example in the tutorial is given A and B that we've already talked about, the two subjective assessments, which one's the prior probability and which one is the posterior or pre-test, post-test?
The selection of the male will be the probability.
Uh-huh.
The male smoking a cigarette will be the posterior.
Exactly. Yep. So that's the language that we're going to use: pre-test, post-test, or pre-test or prior or posterior probability. And so the general formula of Bayes' theorem that's usually given is here. It's the same one in your book. So what you're calculating is the conditional probability of disease D given that some test result R occurs. And so the next thing the book shows you on the same page is they write this equation 2 more times, and they calculate the probability for a positive test result and a negative test result. And that literally just is rolling through and this is general form is for some result. If you want it for the positive result, just take that sum result and make the R's positive all the way through. And so that there's no math involved in doing that and coming up with those other forms in the book. And so basically what it says is you do the probability of the disease and then the probability of whichever result you're looking for given the disease over the probability of the disease times the probability of the result given the disease, same thing as the numerator, plus the probability of not having the disease times the probability of the result for in the population that doesn't have the disease. So let's work in a brief example. So this is also from the tutorial. I specifically took the ones from the tutorial so that you would have the richer text to go back and read through if you're not, if you don't work a lot of base problems. So the example says in Orange County, 51% of the adults are males. So then what percent are females? That's 49%, so 1 minus, because they're assuming 2 outcomes, not that that's necessarily the case in reality. So then if you take one adult and randomly select them for a survey involving credit card usage, they first want the prior probability that the selected person is male. So that's given, right? Okay, good. Everybody with me? Okay. And so then the next question is, it's later learned that the selected survey subject was smoking a cigar. And then they give us that 9.5% of men smoke cigars and 1.7% of females smoke cigars, which is based on some lovely data from SAMHSA. And so then we're going to calculate out, oh, it looks like I missed what we're calculating, but we want at the bottom, we want the probability that the person that was selected is a male, given that they're smoking a cigar. And so the blue are what's given in the equation, or the problem statement. I always write those down first to sort of take an inventory of what I have. So we've got the probability of male is 0.51. Therefore, the probability of not male is 0.49. Then the probability of cigar smoking, given that the person is male, was given as 9.5%. And the probability of cigar smoking, given that the person is not male, is 0.017. So that's just straight out of the problem statement. And then the easy application of Bayes' theorem is just plug and chug, where you substitute those in for what they are in the equation and calculate out the final result. So that's pretty straightforward use of that equation. Where it gets tough is if you have to calculate some of these other things. Where it doesn't give you some of the terms, but you have to calculate them based on other information in the problem. So the key is kind of knowing which of those situations it is. And so the way that I tend to work these, I don't use the big equation because there's often different variants of what people give you in the problem statement. And so I just go straight to the table and the tree. And so for this one, with the cigar smoking, so I pick some large number that'll give me whole numbers. So 100,000, but you could have easily picked 10,000 or 1,000. It completely does not matter. And so if I pick 100,000 in my initial population, it gives me, the problem statement gave me the split of male versus non-male. And so I can divide that 100,000 up into male and non-male on the tree. And then after I've got that, the problem statement gives me the probability that they smoke a cigar given that they're male. And so with the way the problem statement is, I want to walk over there, but I don't want to lose the mic for the people online. So the way the problem statement is that each of these is binary outcomes. And so you know there's two things. So once you know that they're male, because you know the probability that they smoke a cigar given that they're male, that gives you both arms there. So the probability with the smoking cigar and the probability with not smoking cigar. So the not smoking cigar part, that was like not given, you can calculate it from 1 minus, because these are two outcomes, exhaustive mutually exclusive outcomes of one event. Make sense? So like you're using 1 minus to fill out the tree. Then on the bottom arm, for a not male, we take the 49,000 of the initial 100,000, and we're given that the probability they smoke a cigar, given that they're not male, is 0.017. So 49,000 times 0.017 gives you the 833 for the top arm of the tree, and then you use 1 minus, or well, you segregate out. So the 49,000 minus the 833 gives you the bottom arm of the tree. Does that make sense? Is everybody good? Okay. So then if you want the probability of being male given cigar, so that's basically the probability of being male, so that's the number of males over the total cigar smokers, probability of male given cigar. And so that then the blue box here at the bottom, the 4845 are the number of males you can get from the tree or from the table. And then the total number of cigar smokers, you can either get it from adding up the 2 arms of the tree for cigar smokers, or you can put it in the 2x2 contingency table. So like this is the safe, easy, slow way to work the problem. Is everybody good so far? Any questions? Okay, awesome. Okay, so Bayes' theorem does generalize to more than 2 outcomes. So this is an example also from the tutorial that's worked out in gory detail both here and in the tutorial with the multiple outcomes in it. So in this example, it's industrial quality control, where an aircraft emergency locator transmitter that's designed to transmit the signal in the case of a crash. There are 3 manufacturing companies, manufacturing company A, manufacturing company B, and manufacturing company C. A makes 80% of the ELTs on the market, B makes 15%, and C makes 5%. When you add those up, that is 100% of the gauges on the market. And so it goes on to tell you that the gauges made by AltaGauge Company A have a 4% rate of defects. Company B has a 6% defect rate, and Company C has a 9% defect rate. And so first thing we do is write them all down. So there's the probability of the market share for the gauges, and then we can go forward, and the other blue is what the defect rate. So probability of a defect given that it's company A, B, or C. Okay, and so if we want to know, the first step A asks if a gauge was randomly selected from the general population, what's the likelihood that it was made by company A? How do we know that?
Because they make it 80%.
Exactly, it was stated right there in the problem statement. Okay, so that was a gimme. B's not exactly a gimme. So, but it's not hard either because we have our tree handy. So B says if a randomly selected gauge is tested and found to be defective, what's the probability that it was made by company A? And so we put in our conditional probabilities, the second group of blue ones that are given in the problem statement, and we start drawing out our tree. So this time I just picked 10,000, but you could have picked 100,000, it doesn't matter. And so you just pick a population of gauges, and because we know the market shares of each company, we can fill out that in that 10,000, we're going to have 8,000 that are made by company A, 1,500 made by company B, and 500 made by company C. Is everybody good there? Just straight application of the probabilities. Yes?
I'd like to take you back a little bit. I think with the first example we just saw, when we use your formula, like with the denominator, there is no bracket, so one you should just use it straight away. You get a different answer. But what is in the handout, they are all into like in your black brackets. Like the first part of it is in its bracket, and the second part of it is also in another bracket, so that you don't work it out. I mean the first formula you just used.
This one.
Yeah,
Okay.
so, with the okay. Like, I mean, the formula itself doesn't have the, closing brackets when you look at the formula. But in giving
Oh.
the example, you use the brackets. So, in case somebody doesn't look at the example by just using the formula, you're going to get a different answer.
So you mean the square brackets?
Yeah, that's what
Okay, so the square brackets that's how you note a conditional probability.
No, like, I mean, for instance, the probability of a meal multiplying the probability that,
A cigar smoker given male.
Yeah, given meal, it should be in one bracket plus, the other side, which is also to be in one bracket.
So you mean in the denominator
Uh-huh.
on the bottom? So because of order of operations, I put the parentheses down there on the bottom, but you don't have to because of order of operations, the multiplication always happens first.
Because, I don't know, but if you should just, make it straight away,
Yeah.
you're going to get like a different answer without the brackets.
So do you want to work it on the board?
Like, I mean, on the handout,
Yeah.
they have, brackets indicating that those two, like, cannot be calculated straight away.
Okay, these ones?
There is, see, this a bracket encompassing the first part, and after that, a bracket for the second part.
So that's the same thing, because the multiplication, so before you add, you have to do this multiplication.
So, like, I mean, with, the formula, with your formula right now, there is no that bracket for people to see that you have to first multiply the first part before you do the second part. That's what I'm trying to do.
Yeah, so there's a rule in math, they call it order of operations,
Yeah.
that you always do the multiplication and division before addition and subtraction. So because of that rule, so I didn't need to put the parentheses on the bottom. I just kind of did it to help visually distinguish them. But because of the order of operations rule, you always do the multiplication and division first.
Oh,
So it's just burn it in that brain.
okay.
Got it?
Like, just to make it
Please
clear.
excuse my dear Aunt Sally.
What was that? So, okay, I forgot.
Please excuse my dear Aunt Sally. I'm not.
Okay, so say it
That's
well.
the order of operations.
Please,
Yeah, I get it.
Okay.
I get it, but I just wanted to, bring it out in case somebody would, get confused about that.
Oh, yeah. No, hopefully you guys everybody's okay with order of operations, right? Okay. Okay. Thank you for bringing that up. Okay, so for B, so we've got our initial population of 10,000 gauges segregated out by company. Then for each company, we have a defect rate. So for company C, the defect rate is 0.09 or 9%. And so we just take 0.09 times 500, and that gives us 45. And 500 minus 45 gives us the number that would be defect-free from company C. Everybody good with that? Okay. And then you just do the same thing for company B and company A. And that fills out the whole tree. And so what part B is asking is to calculate the probability that a gauge was made by company A given that it's defective. So down here at company A, we know that there's 320 defective gauges at company A, and the total population of defective gauges is 45 plus 90 plus 320. So we're adding up the total number of defects across all three organizations, and we have the defective ones from company A in the numerator. And then when we just multiply that out, that gives us 0.703 for the probability that a defective gauge was made by company A. Everybody good? Okay. There is for easy use, the book also goes over use of likelihood ratio, which is the probability of a result given disease over the probability of a result given not disease, which corresponds to the post-test odds equal the pre-test odds times that likelihood ratio, because the P of R given disease is the odds. So you can also use this. There's, I think, an example in the book about it. I do it the other way just because it's very straightforward and explicit. And so would you guys like to work some more on the whiteboard now that we have gone through problems, or are you guys good?
Blackboard.
Okay, whiteboard. Okay, so for those of you online, I have posted, there are two things posted in the folder for the week. There's the tutorial with the problem statements, and then there's also the solutions in handwritten stuff for the problems so that you can follow along. I apologize for the chicken scratch handwriting, but I wanted you to have the solutions. Not all the solutions were in the back. Okay, hang on, guys. We got a ding. Okay, good. Michael's got them. Okay. Okay, so who wants to pick a problem? If you go to page 7 in the tutorial, those are the problems. And I think I brought markers and pens. Okay, so for those online, you might not be able to hear as well, but we're going to work them on the board, but you have everything in the handout. So hang on, let me turn off the overhead. There we go. Okay. So do you guys just want to work problem 1? Okay. So does somebody else want to come up here and work it?
We're going to have to do it in R while we're
All right, Robert's going to go. You want to come up and do it? You be the scribe. We'll tell you what to write. That'll take the pressure off. Okay. So in problems 1, they give us a table, the 2x2 table, for pregnancy test results. And here's an eraser if you need it. And okay, so part A says if one of the 99 test subjects is randomly selected, what's the probability of getting a subject who is pregnant? Okay. Yeah, there you go. Okay,
So total.
I think it's 3 in the bottom one.
No, I changed the table because in the handout, the pregnancy is here. If you look at it. And the result
Oh,
is
okay, I got it. I see.
here. Yeah, so. 23.
So looking at A and I.
Yeah, so that's what we were just talking about, Felicia. In the example, they switched what was on the top and what was on the side. It was tricky.
So you will be the total, which is
99.
99.
Yeah, there you go. Okay, so A says of the 99 test subjects, if one of them is selected, what's the probability of getting a subject who's pregnant?
Okay, so who is pregnant?
So the pregnant ones are the true
These
positives.
are the pregnant ones, so it's gonna be 85 over the total, which is 99.
Yep.
And,
Which equals 85.9%.
85.9%.
Yep, exactly. Okay, so then the next part says a test subject is randomly selected and is given a pregnancy test. What's the probability of getting a subject who is pregnant? So the probability of pregnant given a positive test.
Okay, so the test subject is randomly selected and is given a pregnancy test. What is the probability of getting the subject who is pregnant? So probability of being selected.
So probability of pregnant. Yep, given a positive test.
Oh,
Everybody got that? So when it says in the question, it says, what is the probability of getting a subject who's pregnant? So the probability of pregnant,
oh, given the test result is
given the positive test result, exactly.
so what is going to be of the pregnant condition of pregnancy. The P with like about it is not pregnant.
Exactly, yep.
And probability of not pregnant condition.
Oh, okay, I was gonna project it for you, but that'll screw up. So here you go. So, probability of pregnant and then probability of
Pregnant.
so if you want to, so this would be probability of pregnant given a positive test. So this is the probability of pregnant times the probability of a positive test given pregnant.
Oh, okay.
There you go.
Uh-huh.
Okay, awesome.
Yeah.
There you go. And then over that same thing. This way. Yeah, there you go. Then the probability of not pregnant, which you got, times the probability of the positive test given not pregnant.
Oh, okay.
There you go.
All right. So probability of pregnant is this. Probability of positive test given in the this is pregnant. This is going to be and positive and pregnant. Positive and pregnant, 80 over pregnant, 35. Please, can somebody calculate this for me?
Yeah. .9412.
0.9412. Okay. Let me see what do I need. I already have this. I have this.
So you need them, yes, that one.
Probability of not pregnant. Not pregnant, 14 over this.
So that's .1414. Yeah, repeating.
0.1414.
Yep.
Probability of positive test not pregnant. So positive test. Positive test not pregnant. Which is
So the
test not pregnant. Over probability of not pregnant, which is 14. Over 14.
0.2142. Well, 0.2143.
Okay. Okay. So right now I have everything I need. So probability of pregnant positive test will be. This is going to be 0.859 times P 0.9412 over 0.859 times 942 plus no pregnant, which is 0.1414 times 2, 0.2143. I think I'll need a calculator.
Okay, hang on, can't get to my calculator yet. Well, here, I'll get to this one. There it is. Okay, which is 0.859 times 0.9412. Okay, so that gives 0.8085.
0.48.
8085.
And okay, so this one will be the same 0.0805 plus 0.1414 times 0.2143.
Okay, hang on. So that was, I think I called it out to you wrong. It is 0.8085.
0.8085.
Yeah, and same thing on top. Point. There you go. I don't want to screw up. Okay, then the other one is what? 0.14. 0.21. 0.0303.
0.0303.
Yep.
Okay, so the final 0.8085 plus 0.0303.
Okay, 0.8388. Yep. So, and so the final is 0.8085, right? Divided by
Yeah,
0.8388. Oh, shoot. Sorry. 0.8085 divided, 85 divided by 0.83. So 0.964.
0.964.
Yay.
Woo! Is it a same thing?
Yeah.
Oh.
Okay, who wants to work? You want to work another one?
What?
Another way? Yeah. You want to show the other way? No. Yeah, it's there is a simpler way, but I won't discourage people from using the formula should they want to. But no, go ahead and show. It's okay. Show here.
Is that you translate this thing, what is probability of, this is a pregnant, so all the pregnant here, they are 80 over the positive, which is all the positive here.
Yep.
80 over 83, it will be the same answer.
So those are the two ways, right, that we did in class earlier. We did using the Bayes, the long form of the Bayes that you can use. That's there for you. It's the law. It works. Or if you go, go straight to the table or the tree to work. Either way, it's completely fine. Okay. Anybody want to work another one? And I think in the handout, the solutions, yeah, I've got the solutions for all of them in the back. So.
You almost look like pizza on that very much. P's, A's, and Z's.
Oh, yeah. You want to pick, they have one in here with sensitivity and specificity in it, I think. Yeah, so they have a number 9. They've got an HIV test in here. You guys want to work number 9? Or if not, we can work another one.
Are you going to put it on the board?
Yeah, if you guys want to work, you guys pick. This is for. All right, who wants to come up and work it? Nobody? Oh, come on. Somebody's got to come up here and work it. We will all help whoever comes up here and works it. Nobody wants to come up here and work it? Okay, guys, I guess we don't have a volunteer. Number 9. Okay, Miriam. So for number 9, I would encourage you to go to the tree first. Okay, so let's write down all the givens here. I'll do more cleanup for you. Start writing down the givens and I'll get this cleaned up. Oh, maybe we can keep this table. So it's, is this 10% is just in general, it's not associated with the tech. Yeah? Okay, so let's see what it says. The State Health Department reports a 10% rate of HIV virus for the at-risk population. Okay, so this, our population might not be the whole population. They just might.
They want it out of
Yes. So let's just say we're dealing with an at-risk population. So under certain conditions, a preliminary screening test is correct 95% of the time. So should I do a tree thing? Well, let's write the givens out first. So the first given is the probability of HIV in the population versus not HIV. Yep, there you go. Given the, just general, in general. Yep, that's this one. Yep, so probability of disease is 10.
Sorry.
I can't keep up with you. Okay, all right, there. So then probability of not disease is the, yep, there you go. Okay, and then what else do we got? The probability of actually being positive in screen. What's the test correct? Okay, correct 95% of the time. So here you might need this. This is the probability of a positive result given. Wait. The probability of disease given a positive result. 95%. Okay, so the way that I did it is I did the probability. You can, if you assume that correct means accuracy, then it's the true positive plus true negative over everything.
Yeah.
But their language in the problem is a little loose. This is always a little bit stuck. Like I can work this once I have this. It's just given. Okay, so let's go. Let's do easier. Right. Oh. And probability is not correct. And then it tells us here from this population, randomly selected from at-risk population, what's the probability that they have HIV? So probability of disease given a positive test. Yeah. Use C. Well, no, just positive test. See, they give you the correct. See, we have to back out the numbers that we need because they don't give us all the numbers that we need. Positive. Yeah. Okay, so then let's start drawing the tree. So we got 90. Okay, so let's use 1,000. Yeah. Okay, so there's 1,000 patients in the population. So then the probability of HIV is 100, and then the probability of non-HIV. Yeah, and then so out of that, let's see.
Okay, so then we go back over here. So, let's see, what did I do last time? You don't just know. So this is 1,000. So is this all the way down? Is that really this percentage? So is that really this percentage? So the way that they state it, this would be over all of them. Well, just put them all. But that does not help me as much, because it doesn't help us back it out.
Yeah.
And so when they do it in Bayes' theorem, they assume that the probability of correct equals the probability of positive test given HIV. They just assume the one. So probability of positive test. So they're assuming that it's the sensitivity when they do that. They assume this number? Yes. So this is the sense. Okay. So then over here, we have the 95. Yep. And then that would be 5. This one would be okay, then so hang on. Okay, so this, I think they're assuming that the false negative is 0 when they do it here. Because if we have, so we got the sensitivity, so we have this one.
So how do I know, because you said that they're assuming that this, is this, in this case, if I get a problem that always has it stated this way, is this always going to be sensitivity? Or are there going to be cases where it actually equals, where the true negative is?
So I think they mean sensitivity when they say that, even though they say accuracy. Even though they say correct. I think they don't mean what they said, which is this. I think they mean sensitivity. And so then when they say here that it's not correct over here, so then if it's, so then when they tell us it's correct here, we do the sensitivity, we assume that it's not correct 0.5% of the time, which is probably about this. Yeah, so then we assume, no, this is the 1 minus. So here for not correct, which would mean that if they have 900 that are not HIV, and it says they're positive, so then this would be the 0.05. So then with the tree, yeah, this is all this, yeah. It's the language is a little loose. They have the same problem I have. So if we, so the problem is not correct, yeah, there we go. No, it's too much. Here, I'll do 0.05. Sorry for you guys online. I know this is incredibly boring. Okay, so 0.05 times 900. 45, yeah. And then 900 minus 45 is 885. Okay, so now they want to know what is it?
Yes, how do you write it? So the probability of disease. Here, I'm gonna make this bigger so people can see. So probability of disease given positive test. So if we put these in, so the probability that they have disease is, so these are true positives. These are, let's see, they have it and it's negative. So these are, I think, false positives. No, it's negative, so these are false negatives. There you go.
False negatives will be the ones that test positive.
And then these ones are the non-ones. So these are the false positives here. And then these ones are true negative here. So when they want the probability of disease given a positive test, so the probability of the disease is this, equals 0.1. And the probability of positive test will be this plus this. Plus 45. Okay, so positive test, so probably.
Yeah, you're on the right one.
Well, come on up here.
I think when we use the first formula, we should be able to get it.
This is the ones. That's the 100. The 100, yeah. Because this is disease. This one. Yeah. So there's that, and then the positive test is these. So let's see. Better with the box than the truth. Yeah.
Well, you can make a box, make a box. So,
So 140.
okay, so yeah,
You see the answers to these?
they're in the back.
Oh, in the back.
Some of them are in the back.
But I think we can still use the first formula and we will still get it.
Well, yeah, but we're trying to work it with a tree.
The tree? Okay, so.
We're trying to figure out the language in the.
So we have 1,000. Okay, that's the 10% of the bucket. So from 10%, we know that 95, okay, sorry, so 95, yeah, 25, just 25, so okay. So this one will be 85. So from here. Those aspirates and testing okay, those aspirates. So those aspirates. Yeah, this one, 95.
95.
Yep.
What is the box? Is this? So close to.
So yeah, 95. There you go.
So is that right?
Yeah.
That gives the right answer?
Yeah. The right answer.
This is why I go to genetic.
So 95 divided by 1 is where I get.
Yep, so 95 divided by 140, it's 67.9.
Yeah, so,
Yeah.
so you're right. So 67 point, oh, 67.
0.9.
Oh, okay, so. Which is the same as the 0.67.
So now we need to figure out why the tree.
Yeah, the tree, right?
Right.
The tree is right.
But that 100, right? So it should be
Yeah.
the 95 versus the 100 instead of 95.
Oh,
Because you have the 100 over 95. You just, it was just like a, does that make sense?
yeah. Okay. So then for these, when they say the probability of correct and not correct, you have to read in sensitivity and specificity, not accuracy. Because when they say probability of correct, you think it's the true positive plus the true negative over the whole thing. You guys want to do another one? Oh, sorry. Okay. I've actually got to go do this over again.
I'll probably go watch some YouTube videos and find the.
Yeah. So there.
Make a matrix and data or something.
Yes, we could have easily. Yes, correct. If she positive predicted value. Probability of disease given test. See here? Yeah, which is the 95. I mean, are you just going to do it for? Yeah. So there are 9 problems, 10 problems, something like that in the tutorial with the solutions so that they. Okay, guys, those of you online, we are breaking up.